Okay, so today we will prepare a little more for talking about root data. So Borel subgroups and parabolic subgroups and maximal tori. So for now, I will actually assume that G is always connected unless it's explicit said otherwise. Maybe I just highlight this. Okay, so now let's start with some definitions. So a Borel subgroup of G is defined to be a maximal connected solvable subgroup. So yesterday we said that somehow these connected solvable groups are important for us in studying linear algebra groups. So now maybe just these groups do exist because of dimension reasons. And then, of course, then they are closed subgroups. Or maybe it requires a little bit of thought. So now what about the examples? And so what would be, for example, G equals to G of N? What do we think the, at least a Borel subgroup would look like? So we usually write B to be the, to be a Borel subgroup of G. Any upper triangular? We know that is connected and solvable, right? So maybe we don't yet know its maximum. So you can also, of course, take B minus to be the lower triangular matrices. This is also a connected solvable subgroup. So now a theorem about these Borel subgroups is that so the Borel subgroups are actually all conjugate to each other under G. So secondly, so if B is a Borel subgroup, then turns out this quotient variety G mod B is a projective variety. So today I'll still do a few scheduled proofs. I think tomorrow there will be no proofs. So, okay, so how do we say that the Borel subgroups are conjugate to each other, and why is G mod B a projective variety? So the idea is as follows. So you can take a Borel among all Borels so that it is of maximal dimension. So now, again, when we discussed quotients, we said that there exists some rational representation of G so that you can realize this subgroup B as the stabilizer of a line. maybe okay. So L is a line in V, or it's a point in the projective space of V. And moreover, so this part we didn't discuss in detail, but so supposedly there will be this isomorphism from the quotient variety to the orbit of L under G. So now what we are gonna do is, last time we discussed Borel's fixed point theorem. So if we use this theorem, which says that the connected reductive group acting on a projective variety has a fixed point, so we can use this term repeatedly. Then we will find we can extend this L to a flag. So that this B actually becomes the stabilizer of this flag here. Okay. So now we write this flag to be W. So this now is a point in the flag variety V. So now making use of this, we get a map from G mod B to the orbit of G. So Gx on this flag via your representation rho. So we get a subvariety of Fv. So there are two claims. So claim one is that this is an isomorphism of varieties. So you make use of the fact that this is already isomorphism, and then there is a natural map from this to here. Well, you need to think about it a little bit. So now, second, so if we wanted to prove that G mod B is projective, so we are already isomorphic to something inside the flag variety, which is projective, although I didn't prove it. So we need to show that G mod, this orbit is a closed orbit. So after we establish this, then we know that the G mod B now is a projective variety. Okay, so I'll briefly see the idea of the second point. So if you have another point in your flag variety, so that the stabilizer is GW prime, so. So should be GLN mod B? No, G mod B. Like in the flag variety? No, G. Like we know the flag variety. So here the action is via rho G, right? So rho G becomes an element in GLV and it acts on the flag. So I really want to prove G mod B is a closed subvariety of FV, right? Oh, the question was should it be GLN act on W, but we want G act, but okay, so this is, so GX via rho G. So similarly, G act on the flag manifold via the representation rho. So because the stabilizer fixes W prime, this means rho G W prime, this is the isotropic group, is solvable. So now kernel of rho by construction is contained in the Borel, so it's also a solvable group. So now you conclude that GW prime, the stabilizer, is also a solvable group. But now, fortunately, we have already assumed that B is a Borel of maximal dimension. So you know that the identity component of this stabilizer group is less or equal than the dimension of the Borel we chose. So now we know that the dimension of the orbit is equal to the dimension G minus dimension of G W prime 0. So this is greater or equal than. So this shows that my orbit is really a closed orbit because it's minimum dimension. So then G dot W is projective. So now we have shown that G mod B is indeed projective for the B that we have chosen. So now, what about any other Borel subgroup? So if I take another Borel, so then what should we do now? to kind of, we wanted to conclude that B prime is conjugate to B. What do we think we should do now? So we already proved G mod B is a projective variety, right? And by the way, G mod B is also called flag variety for G. So any thoughts? Very good. So then B prime will act on G mod B has a fixed point. So this action is just by a left multiplication. So this means, so there exists some coset so that okay, so this is now a kind of you conclude B prime is contained in the conjugate of B, but B prime is maximum solvable. So then we conclude that B prime is equal to G inverse BG. So conjugate to B. So now we proved both in somehow together, both statements. So now a corollary of this is the following. So if you now have another closed subgroup of G, then the quotient variety is, so before we say that it's a projective, a quasi-projective, now it is a projective if and only if P contains a Borel subgroup. Okay, so I'll leave this corollary exercise. Yes.
Why if you take P prime in the previous another model, it acts on G mod B? What is that?
Oh, action is just so question is what is the action of B prime on G mod B? Action is by left multiplication.
And is that what the
Huh?
And why?
B prime G B is equal to B prime GB.
Okay.
Yeah.
That's also. I mean, G acts on that. So, of course.
Oh, yes. Okay. That's a better way to explain. Yes. G X on G mod B. So subgroup, of course, also X. Okay. So now, very good. So now this seems very nice, right? All the borers are conjugate and then closed subgroups so that G mod P is projective are exactly those contain the Borel subgroup. So now we give a definition to these groups. So such a group as in the corollary is called a parabolic subgroup. So now I just tell you that for GLN, maybe some of you guys already know. So a parabolic will always be conjugated to one that's block upper triangular. So of course the size can be arbitrary. So then in some sense, the Borels are a minimum parabolic subgroups. So they are also parabolic, but because they're special, so we call them Borels. So they are the only, actually the only solvable ones. Okay, so now we have defined Borel and parabolic. So one more ingredient for the discussion of root datum. So now a maximum torus. And last time we also discussed what the torus is. A maximum torus of G is a subtorus. Well, I guess it's probably obvious what it means. So it's a subtorus not strictly contained in another one. So then another concept that it's enough is, sorry, not enough. It's important for some of the proofs is the so-called Cartan subgroup. Of G is defined to be the centralizer of, identity component of the centralizer of maxima torus in G. Okay. So now, before we move on to structure of some property of the structure of an arbitrary linear algebra group. So first, I will state some things about the structure of connected solvable groups, but without proving them. So theorem. So now G, in this theorem, G is connected and solvable. So first of all, so the GU, the elements of the unipotent elements in G form a closed connected normal subgroup of G. And also this GU will contain the commutative subgroup, commutator subgroup GG. So moreover, sorry. And also the G quotient GU now is a torus. So we can maybe just think about, for example, first the upper triangular matrices. So this first statement seems okay, right? So now if moreover G is nilpotent, abstract group, then we have a similar decomposition of G into a semi-simple part and the G unipotent part. So connected nilpotent group can be decomposed the same way as for commutative groups. So this just says GS is now a central torus. Now, something else about connected solvable groups is that every semi-simple element lies in a maximal torus. Oh, okay, this is a lot of conclusions about this connected solvable group. So if you take a semi-simple element, then its centralizer in G is connected. So, so this is not true in general. As you will see in the exercise, if G is not solvable, then this is not true. Okay, and then there are some kind of non-trivial facts. So any two maximal tori of G are conjugate. And now if you take a maximal torus of G, then we can have a morphism from T cross GU to G, and turns out this is an isomorphism of varieties, but not of groups, as we know, right? In the upper triangular matrix situation, you can take the maximal torus to be the diagonal matrices. It doesn't commute with the GU, so G is not a product of T and GU, but we will see that this is a semi-direct product. Sometimes we write it like this. So one more. So if H contains G is a subgroup, consists only semi-simple elements. Then H is contained in a maximal torus. Moreover, the centralizer of H is the same as normalizer of H. So before, from rigidity of diagonalizable groups, we know that the connected components are the same. But in this case, this group is they are both connected. So this is connected. So from the statement of this theorem, we see that the maximum torus of G has dimension equal to what? Is it clear? What was the question? What is the dimension of a maximum torus in a solvable? Okay, maybe that is not a very good question. So, okay. I want to say that so this torus really is kind of it's not in G, but the dimension of the maximum torus is the same as that. GU, yes, yes. Okay, so maybe I just comment on the part G. So why is H a subgroup consisting of semi-simple elements? You can conclude that it actually somehow become diagonalizable. So this is you can look at this map from G to G mod GU, but now if you restrict to H, so then this is a bijective map because all elements in H are semi-simple. So this is bijective. So then you can conclude from here that H is commutative. How to restrict both? Okay, injective probably is enough. Meaning you take, okay, I can take H and phi H, then it's bijective. But so now, as I said, so this proof is actually a bit complicated, at least for some of the statements. So I will skip the proof. So I will refer you to the book of, well, maybe it's just Springer. So this in the section 6.3. But if we assume all this structure theorem of connected solvable groups, we can deduce good things about a connected linear algebra group. Oh, okay, I said from now G is connected, but anyways. So G is connected. So then what we can conclude is that all maximum tori of G, what can we conclude if we think of what we just proved? So we proved all the boroughs are conjugate to each other, right? And now we know that all maxima tori in the connected solvable group are conjugate. So we can conclude that in G, all maxima tori are conjugate. Yes, very good. Oh, is it clear what it means to be conjugate? Yes, okay. So now secondly, so every element of G will lie in the Borel subgroup. So in other words, somehow the Borel subgroups covers the whole group. Huh? Oh, remark. Oh, remark. Oh, yeah.
I don't know how to say remark without rolling my eyes. The dimensional T over U is the subtraction of the dimensions. Is that correct?
Yes, I said yes. So this is equal to the dimension G minus dimension GU.
Okay.
This is what we, I guess we didn't quite prove, but we stated this theorem when we talk about quotients. Yeah. Okay, so then now every semi-simple element of G also lies in a torus, a maximal torus. And 4 says that the union of all Cartan subgroups contains a open dense subset of G. So now 1 and 3 kind of follows already from the property of, right? So, from the property that, okay. So maybe again, some sketch of ideas of the proof for this theorem, assuming the structure of connected solvable groups. So 1 and 3 follows from Borel's conjugate. And then structure of connected solvable groups. So then what about the 2 and 4? Hmm? Say that again? No, now G is just a connected, maybe I just write it all out. Connected linear algebra group.
I was just confused about point B of like using the structure of connected solvable groups.
Oh, so because so to prove every semi-simple element of G lies in a maximal torus, I wanted to use the fact that so okay, let me see. Maybe you're right. No, maybe I actually sorry. So I think I need to first prove 2, right? And then I probably can. Okay. Only 1 follows. Sorry. Thanks, Grace. So sorry. So yes, 1 does follow from this. So okay. So now let's see. If I can prove 2, then I can prove 3. So I want to comment on the proof of 2 and 4. So there is a lemma as follows. So if you have H contained in G is a connected closed subgroup. So now you can look at the union of its conjugates. So the idea is that then this X will always contain a non-empty open subset of its closure. And if this group H happens to be a parabolic subgroup, then X is closed. And part B of the lemma says, now if the normalizer of H in G quotient out by H is finite, and there exist some elements of H lie in only finitely many conjugates of H, then we can conclude that the disclosure is actually G. So, okay, so these two lemma will help us prove the point 2 and 4. So let's.
Could you just restate the, like, when we say there exist elements that lie finitely conjugates? Like, like what is the, so with question B in part B, NGH on X is finite and what?
And there exist, let's see, an element of G, so H in H, which lies in yeah. So so the proof goes as follows. So okay, so let's take a subvariety of G mod G cross G as follows. So XY in G cross G, so that XY X inverse is in H. So this is a closed set in the product of G and G. And this is also isomorphic to G cross H. So this is irreducible. So now we wanted to look at the map from G cross G to G mod S cross G. Then we look at the image of this Y1. So this becomes something called, we call it Y. So this becomes XH and Y in G mod H times G, so that XY X inverse in H. Now, then our X is the image of Y under P2, where P2 is the projection from G mod H cross G to G. So then we again use this fact from algebra geometry. So X contains a non-empty open set of X bar. But now if H is parabolic, then we know that G mod H is projective, and so again, some algebra geometry fact that I didn't prove, but I put it in the exercises if you. So that the P2 is a closed map. So then we conclude that the image X is really closed. So now what about, so this is part A. So now part B. Again, this is a sketch. So we look at the variety Y that we just looked at, and we project to G mod H. So what the condition tells us that there exists some X in sorry, what? Sorry, so we consider a P2 from Y to X, right? So, or to G, to X bar. So there exists some X in H so that the fiber of this map is finite. So then we can conclude that, again, use some algebra geometry fact. So dimension of X bar is equal to the dimension of Y, and then this is equal to dimension of G. Okay, so because of a time constraint, so I think I'll leave this lemma to you to think about. So to prove this number 4, for example, so no, sorry, to not. So anyways, so to use this lemma, I still need something like this. So I wanted to apply this lemma to H to be the Cartan subgroup. So lemma one needs to prove is there exists a T in the maximal torus lying in only finitely many conjugates of C is the Cartan subgroup. Okay. Anyway, so this theorem somehow also is not very straightforward. So I'll again let you fill in the details. So now, oh yes, sure. Sorry. Yes, I guess I'm again writing too fast.
If we have G is GLM and T is the diagonal matrices, is it easy to see which torus element does this? Can you see what diagonal matrix is enough?
Yes, very good, very good. So first of all, when G is GLN, the question is for GLN, can we see which T lie in only finitely many conjugates of C? So let's all think about it. What could those, so for T to be diagonal matrices, so we know actually ZGT 0 is itself, right? So we are just asking which elements lie in only finitely many conjugates of T. So if you have some elements you want it to be in G. Okay, maybe I just say something and then you check that it actually lies in.
Is it the matrix with more distinct entries?
Right, so that's probably the best, I mean, that's the most generic element, right? So, yeah, so distinct eigenvalues. So these elements actually also has a name. These are called regular semi-simple elements. Okay, very good. So now, if I have a Borel subgroup of G, then turns out that the normalizer of B in G is just B itself. So similarly for a parabolic, this is also true. Moreover, so you can show that the P parabolic are connected, and the normalizer is equal to P. So, and also there is another corollary. So T, if you have maximal torus contained in a Borel, so then this group we said is a finite group, again because rigidity. So there is a bijection of this with the Borel subgroups containing T. So this will be an exercise. Okay, now finally we get to define what, well, we could define this earlier, but anyway, so definition, so if you have a connected group, define the radical of G to be a maximum closed, connected, normal, and solvable subgroup. And then we wanted to define the unipotent radical denoted by RUG. This is a maximum closed, connected, unipotent subgroup. So this group is, the unipotent radical is equal to the unipotent unipotent radical of RG. Or the group as before, so GU. Oh, I think so, right? Otherwise, this is thank you. No. Hmm?
In both 1 and 2, you wrote as any maximum close maximum. You actually identified it as when you find a classical.
It is. Oh, sorry. So in the definition, I said is a maximum. So no. So let me write down actually it's easy to see what the RG is. So I guess if you have any such group, you can generate a bigger one. So the RG is very good. Thanks, Martin. So we see, maybe I should have said. So it's the intersection of all the Borels, and then you take the connected component. So, and then I can just move this here. Okay, so I let you think why RG is this. And now a definition, so a connected linear algebra group, G is called semi-simple. If its radical is just trivial. So this semi-simple is not has nothing in some sense to do with our Jordan decomposition, unlike the unipotent groups situation. So it's called reductive if the unipotent radical of G is identity. So then a remark as an exercise. So if you have any G, so then you can mod out by its radical, then you get a semi-simple group. And if you mod out by its unipotent radical, you will get a reductive group. And then if you have a connected solvable group, is reductive. If and only if G is a torus. So I guess I'm out of time. So let me just write down some examples. What do we think? In the groups that we have seen, which ones are reductive? Torus. Okay, very good. That's exercise 2. Torus are reductive. Are they semi-simple? What else? Huh? Oh, for round? Are they reductive? No, wait, but what is the definition? You want there is no maximum, I mean the maximum closed connected normal unipotent subgroup to be trivial. For the upper triangular matrices, that's not true, right? Because we said that the unipotent part is okay. So
this is, I think, really important to discuss in the also in the problem sessions. Write down whatever group you can think of and discuss if it's reductive or semi-simple.
Very good. I'll put that in the exercise. So should I then not tell you anything?
We're out of time, so
okay then. So we'll think about it in the problem session. I'll stop here until.
questions for Ting?
Oh, should I stop share?
No,
Are
it's
people
okay.
still writing?
Anything from Hawaii?
No.
Okay. All right. So we have a break for 35 minutes.
Great.
Yeah. Thank you, Ting. Thank Ting again.
Thanks.